16 to 20 marks in JEE 2025, that too from just 4 chapters. All-time easiest chapter to revise. Units and measurements, motion in straight line, motion in plane, and laws of motion. Yes, you guessed it right. These are the chapters we are going to revise today. Welcome to another recap video of JEE Mantra 2025 series. Moving to the very first chapter, that is units and measurements. Here we are starting with measurement, physical quantities and units. Measurement, physical quantities and units. That are the three things that we are going to discuss right now. Okay, measurement is just comparing any physical quantity with its standard unit. That is what we call it as what? Measurement. Next is physical quantity. Okay, physical quantity is any quantity that can be measured directly or indirectly. That is the standard definition that we consider for what? Physical quantity. And what about the unit? Okay, the standard value of any physical quantity. I repeat, the standard value of any physical quantity which is used to measure that physical quantity is known as what? Its unit. All right, moving to the next. What are the fundamental quantities and their units? Fundamental physical quantities, as you all know, as per the SI system, we have got 7 fundamental physical quantities. And here comes the first one, that is length. Its unit is meter and is represented by m. Next is mass, unit is kilogram, represented by kg. Next is time, unit is second, represented by small letter s. Next is electric current, unit is ampere, capital A is the symbol. Next is thermodynamic temperature, unit is Kelvin, represented by capital K. Amount of substance, unit is mole, symbol is MOL. Luminous intensity, the unit is candela and the symbol is CD. Alright, now the supplementary physical quantities. In supplementary physical quantities, we have got 2 in the list. First one is plane angle and second one is solid angle. The unit of plane angle is radian, symbol is small letter RAD, and for solid angle the unit is steradian and the symbol is SR. All right, moving to the next, derived quantities. All physical quantities which are derived from fundamental physical quantities are known as what? Derived quantities. And along with the name, I mean, we can't explain or we can't mention about all the derived quantities over here, but most important, almost all derived physical quantities are in the list along with their units. Okay, now before that, other than SI system, of course we will be discussing about SI system also here, but other than SI system, what all were the systems that were popular earlier times are CGS system, FPS system and MKS system. All right, in CGS system, the length was represented in centimeter. All right, mass was measured in terms of gram and time was measured in terms of second. Another one is FPS system. There the length was measured in terms of foot and mass was measured in terms of pound and time was measured in terms of second. That is FPS system, foot, pound, second. Next is MK system. Okay, this MK system was the one which was more popular before we upgraded to the SI system. There length is in meter, mass in kilogram and time in second, MKS. All right, and SI system, this is the one what we are following right now. And now out of the fundamental physical quantities, okay, we are going to select few and we will be considering some other units of the same physical quantities. Okay, first come length. Fine. So as per the SI system, the unit is meter, and here I have got another famous unit, that is 1 micrometer, and that is 10 to the power minus 6. Next is nanometer, 10 to the power minus 9. Another one is Armstrong. All right, while dealing in atomic physics and nuclear physics, all this particular unit is very popular. Fine, there it is, 10 to the power minus of 10. Next is for mass. All right, as per SI system, it is kg, and 1 metric ton is 10 to the power minus 3 kg. 1 pound is 0.45359 kg. And next is 1 AMU, that is atomic mass unit, that is 1.66 into 10 to the power minus of 27 kg, and rounding off it is 1.67 also approximately. Next is volume, and here we have got volume. I mean, the volume is a derived physical quantity and the unit of that is going to be meter cube. But here I am considering another unit, that is liter, and 1 liter is 10 to the power minus 3 meter cube. This is again very important. Like you will be especially dealing with this in fluids as well as in KTG as well as thermodynamics also. That particular part is very, very important. I repeat once again, 1 liter is 10 to the power minus of 3 meter cube. And next one is about force. And force, and here we are having this another unit. This is in CGS system, that is 1 dyne, and there it is 10 to the power minus of 5 Newton. Another unit of force is kilogram force, especially related to the weight and all. You are going to come across this particular unit, and 1 kilogram force is 9.81 Newton. Moving to the next, that is pressure. Okay, these all are derived physical quantity. That means from volume onwards, we are moving to the next, that is derived physical quantities. These two are the only one in fundamental physical quantity that you know. And here we are having pressure. The units I am considering over here is 1, 2, 3, 4. 4 units you have. All right, and all the four are pretty very, very important. Fine. The first one is 1 kilogram force meter square, isn't it? Fine. Now here this is per meter square. All right, it's not hash, it is a 4 words like that, means it's divided by area. All right, and there the unit is 1 kilogram force is going to be 9.81 Newton per meter square, and 1 millimeter of mercury. Next is for pressure, that is 1 millimeter of mercury, that is 133 Newton per meter square. Next is 1 Pascal, that is 1 Newton per meter square. And next is 1 atmospheric pressure, that is 76 millimeter of mercury, or 101.325 Pascal, which can also be written as 1.01 into 10 to the power 5 Pascal. Next is for work or energy. Work or energy, work as well as energy both are going to have the same unit only, and here we are having 4 in the list. All right, first one is erg. 1 erg is 10 to the power minus 7 joule. Next is 1 kilogram force meter. It's not upon meter, it is 1 kilogram force meter, that is 9.81 joule. Next is 1 kilowatt hour, that is 3.6 into 10 to the power 6 joule. Next is 1 electron volt, that is 1.6 into 10 to the power minus 19. And this is very, very commonly used unit in electrostatics as well as in dual nature of radiation and matter. All right, and again in the chapter atomic physics as well, isn't it? So 1 electron volt, I repeat, 1 electron volt, that is 1.6 into 10 to the power minus of 19 joule. Next is power. 1 kilogram force meter per second, that is another commonly used unit for power, that is again 9.81 watt. Next is 1 horsepower. This is again a commonly used unit for power. All right, 1 horsepower is 746 watt. Okay, next is Fermi. Nuclear physics, this unit is widely used, and 1 Fermi is 10 to the power minus of 15 meter. Next is 1 X-ray unit, that is 10 to the power minus 13 meter, and 1 astronomical unit, that is 1.49 into 10 to the power 11. That is basically the average distance between the sun and the earth. 1 light year, distance traveled by light in 1 year, that is 9.46 into 10 to the power minus of 15 meter. And next one is 1 parsecond, that is 3.08 into 10 to the power 16 meter. In terms of light year, that is 3.26 light year. And here I have to tell you something very, very important. 1 parsecond. Here, if you closely watch the name of the unit, it has got a similarity with the unit of time. But always remember one thing, parsecond is not the unit of time, that is unit of length. Okay, next is dimensions. Basically, to represent any physical quantity, how many times fundamental physical quantities are considered there or used there. Okay, that is fundamentally we say dimension of a physical quantity. Fine, that is the basic concept behind dimensions. All right, and here I am having a list of 11 derived physical quantity here. Starting with the first, that is area. Okay, area is dimensional formula for area is what? L square. Next is volume, that is L cube. Next is velocity, LT raised to minus 1. Acceleration, LT raised to minus 2. Force, MLT raised to minus 2. Work or energy. Work or energy, in the previous slide also I told, work as well as energy both are going to have the same unit. So same will be the dimension. There it is going to be ml square t raised to minus 2. Next is power. Power is work upon time. So here it's going to be ml square t raised to minus 3. That means here it was 10 to the power minus 2. Here this is going to be 10 to the power minus 3. Next is pressure or stress. It's force upon area. So you can directly take the dimensional formula of force divided by area. There is going to be ml raised to minus 1 t raised to minus 2. Next is linear momentum or impulse, that is mass into velocity, that is mlt raised to minus 2. Next is density, that is mass by volume, that's going to be ml raised to minus 3. And strain, that is a dimensional physical quantity because strain is change in length upon original length. So length is having dimension as L and change in length is also going to have the dimension as L only. So it's basically a dimensionless physical quantity. All right. Next, the new list comes here, that is from 12 to 24. There, modulus of elasticity, it is going to have the same dimension as that of pressure, that is ml raised to minus 1 t raised to minus 2. Okay. Next is surface tension, that is force per unit length. That's why it is m t raised to minus 2 because L and L will cancel each other. Here this is velocity gradient. Velocity gradient is nothing dv by dx. There you are going to get it as t raised to minus 1. I repeat here, this is dv by dx. dv is L t raised to minus 1 and on the denominator you are having L. L and L will cancel each other. You will get t raised to minus 1. Next is coefficient of viscosity. I am not going to tell about the derivation of that because it has got too many physical quantities over there. But the dimensional formula is ml raised to minus 1 t raised to minus 1. Gravitational constant, find F is equal to G m1 m2 by r square. From that formula you can derive this. Here it is m raised to minus 1 L cube t raised to minus 2. Yes. Next is moment of inertia, mass into perpendicular distance square. That's why it's going to be m into L square. Here this is angular velocity, d theta by dt. D theta is dimensionless, so it's going to be t raised to minus 1. All right. Don't miss this. Both of these are having same dimensional formula. So this type of stuff you may expect in what? Match the following questions. And here angular acceleration. If angular velocity is having dimension as t raised to minus 1, so definitely angular acceleration is going to have the dimensional formula as t raised to minus of 2. Yes. Next is angular momentum, I into omega. We have got what? ml square. And here this is for omega. That's why it is ml square t raised to minus 1. Next is specific heat. Specific heat, it has got the dimensional formula as ml square t raised to minus 2 theta raised to minus 1. And here I am using the dimensional equation for temperature as what? Theta. All right. Next is latent heat, that is L square t raised to minus 2. Next is Planck's constant, that is ml square t raised to minus 1. And the last one is, yes, universal gas constant. And there we have got the dimensional formula as ml square t raised to minus 2 theta raised to minus 1. I repeat, ml square t raised to minus 2 theta raised to minus 1. All right. And next is homogeneity principle. So that was all about the dimensional formulas, all right, of derived physical quantities. And here, and I told this type of cases, that means the comparison, that means those physical quantity which are having same dimensional formula. Okay, so that you must take the list and try to memorize that at your own level using some tips or anything like that. Okay, that will be very, very helpful. And that is a most famous segment in the match the following areas. All right. And next is homogeneity principle. So what basically homogeneity principle says, if you have got an expression as like A equal to B, that means the dimension of this physical quantity, that means A, and the dimensional formula for physical quantity B, both need to be the same. And other than that, if A is equal to B plus C, there the dimension of B as well as dimension of C, because they are what? Adding each other. Between A and C, addition is happening. Am I right? So that means the dimensional formula for B as well as dimensional formula for C need to be the same. All right. Next is significant figures. This is again a very, very, very important area. All right. So regarding this, you must identify in which all cases, the most important part is we need to identify in which all cases 0 is significant and 0 is not significant. That is the most important thing in this segment. Okay. So starting with the first, the point number 1 says all non-zero digits are significant. All non-zero digits are significant. And I told you the concern is always about the zeros. Okay. So let's see. Point number 2 says all zeros between two non-zero digits. So I am going to take it like this: 1002. So here you can see two zeros between 1 and 2. So these two zeros are what? Significant figures. That means here the significant figure is what? 4. All right. Next is all zeros ending like this. I means 1200. Here the significant figure is what? Just 2 only. That means these two are not significant. These two were significant, but these two are what? Not significant. All right, fine. The next one is, let me have it here, 12 decimal 00. So here it was 1200, but here it is 12 decimal 00. In this case, these two are what? Significant. So here the number of significant figure is what? 4. Now I am going to take another case, that is 0.0012. That means zeros just after the decimal and in front of a non-zero decimal. These two are non-significant. That means here the significant figure is what? Just 2. This is the most important 4 points that you must understand while dealing with question related to significant figures. All right. Now comes, what if some arithmetic operations are happening? First of all, we are going to deal with addition. Okay, here we can have two numbers, 4.326 and another one is 1.50. I repeat, 4.326 and another one is 1.50. How many decimal places are here? 3. How many decimal places are here? 2. So in the final answer, you can have 2 decimal places only. So in so here, if I add these two, I am going to get the final answer as 5.826. I repeat, 5.826. Now I am allowed to take only 2 decimal places. So I have to limit here it with 2 only. And just after 2, I have got 6. That means again I have to go for rounding off. Since the number what I am going to drop is greater than 5. I repeat, since the number what I am going to drop is greater than 5. So I have to increase the value towards the left by 1. So the final answer is going to be 5.83. Next, what if multiplication or division is happening? And I'm sorry, this is the same. I mean, like what we followed for addition, the same is going to be for subtraction as well. All right. Now, next is for multiplication as well as for division. For multiplication and division, it's totally different from the concept that we used over here. Here, I am going to multiply 12.5 with 4.125. 12.5 multiplied by 4.125. Here, how many significant figures are there? 3. And here, how many significant figures are there? 4. Now, once I do multiply 12.5 with 4.125, here I am going to get it as what? 51.5625. I repeat, 51.5625. Now, here there were 3 significant figures and here there were 4. And in my final answer, I am allowed to have 3 significant figures only. That means 2 numbers were there, isn't it? Here it was having 3 and here it was having 4. So the final answer must be having the least significant value. I mean least significant figure. And here it was 3. So I need to round it off up to 3 significant figures only. That means I need to limit it with 5. And just after 5, I am having 6. So the number what I am going to drop, again here it is greater than 5. So my final answer is going to be 51.6. Is that okay? Next is rounding off. We already did rounding off here. So, but still we need to tell about the rules over there. First one, if if the number what I am going to drop is greater than 5, like as that what we did over here, the number towards the left need to be increased by 1, and if it is less than 5, you can drop as it is. Okay, so here that is the first one point. That means if it is greater than 1, the number towards the left need to be increased by 1, and if it is less than 1, you can drop as it is. And the next is, if the number that need to be dropped is 5, and is 5 is followed by a non-zero value. I repeat, the number drop is what? 5, and it is followed by that 5 is the number which need to be dropped is 5, and the number followed by that is a non-zero value, then the one towards the left need to be increased by 5. So we have an example here, that is, see, it's 3.55. I repeat, it's 3.55. So if I want to limit it up to one decimal place, that means the one thing I need to drop is what? 5. All right. So then this need to be raised to what? 3.6. All right. And what if 5 need to be dropped and it is followed by 0? 5 need to be dropped and need to be the number followed by that is what? 0. There I have got two cases. Now let me take the two examples that's given over here. That is, first one is 3.750 and the another one is 4.650. So here you can see 5 is followed by 0 and here also 5 is followed by 0. And the number towards the left of 5, this is an odd number, and here the number towards left of 5, that is an even number. And if it is an odd number, then there it's going to be increased by 1, and if it is an even number, there it's going to left as it is. So here the final answer is going to be 4.6, and here you may say, you can see here it as what? 3.8. So this is how we do round off the values up to the given number of significant figures. All right, moving to the next, that is errors. Fine. So we are not going to, going in depth to what are the type of errors and all. So regarding the JEE syllabus part is concerned, the most important areas what I am going to tell about is, first one is about absolute error. Okay, so to find out the absolute error of any given set of measurements, first of all you have to take the mean value. Okay, if true value is given, the case is different. If true value is not given, then you have to take the mean value. So here I can have A1, A2, etc. up to AN as n number of measurements. Okay, then I told you if true value is not given, the mean value is treated as the true value. Okay, and the absolute error means the difference between the given measurement and the mean value. I repeat, difference between the given measurement and the mean value is known as what? Absolute error. For example, if A1 is a given measurement and A suffix m is a true value or mean value. I repeat, if true value is given, the difference has to be between the measured value and the true value. And if the true value is not given, the mean value is treated as the true value. So there the difference, that is delta A1, that is what? AM minus A1. Alright, another example, delta A2, that means the absolute error in measurement number 2, that is what? AM, that is the mean value minus of A2. Alright, and next is mean absolute error. Here we will be taking the modulus of delta A1 plus delta A2 etc. up to delta AN. That means the absolute error of each measurement, modulus of absolute error of each measurement divided by the number of measurements. That is going to be mean absolute error. Next is relative error. Mean absolute error, I repeat, mean absolute error divided by mean value or the true value. Mean absolute error, okay, divided by true value or mean value, that is known as relative error. Relative error multiplied by 100, I repeat, relative error multiplied by 100, that's going to be what? Percentage error. Okay, so next is, so that was about percentage error. Next is how to deal with the error in different mathematical operations. So first of all, we are going to deal with addition or subtraction. Here I am having an example, that is x is equal to a plus b. For a also, for a I am having the error as delta a, and for b I am going to have the error as delta b. So here it is mentioned, for a it is given as the measurement a. Measurement for physical quantity a is given as a plus or minus delta a, and for b it is given as what? A plus or minus delta b. Now we want the expression for x, or we want the expression for x after considering the error. That means we want it in terms of what? X plus or minus delta x. So now how to get the value of delta x? That is the concern. So delta x is going to be delta a plus delta b. I repeat, delta x is going to be delta a plus delta b, whether it is a plus b or whether it is a minus b. I repeat, whether it is a plus b or a minus b, delta x is going to be delta a plus delta b. All right. And if you go for multiplication or division, let the operation be like x is equal to a into b or x equal to a by b. I repeat, x is equal to a into b or x is equal to a by b. There the relation is going to be like this. Delta x by x, that's going to be delta a by a plus delta b by b. This is how you can connect the relation between delta x, delta a and delta b. Now if you want to get the expression for delta x, that is going to be what? X into delta a by a plus x into delta b by b. That is how you can have the expression for delta x, and then you may finally represent it as x plus or minus delta x. Here also you may have represent it as, again, x as the final representation as x plus or minus delta x. The same thing is applicable here. There delta x was what? Delta a plus delta b, and here delta x is x into delta a by a plus x into delta b by b. And if you have got a different case like z equal to a raised to p, b raised to q upon c raised to r. Okay, this is again a most important area. If this is the case, now how to get the relation between the errors? That is, here the power of z is 1. I repeat, power of z is 1. So there it's going to be delta z by z raised to 1. Delta z by z raised to 1 equals, here the power is what? P. That is delta a by a raised to power p. Delta a by a times p. That means the power over here, that will come towards the left. So delta a by a into p plus q times delta b by b, because here the power is what? Q, isn't it? So q times delta b by b plus, what is the power here? C raised to r. That's going to be r times delta c by c. This is how we connect the relations. Next is chapter number 2, that is motion in straight line. Okay, so here we are starting with motion, rest and point object. Okay, so the first one is motion. So a body is said to be in motion if the position of the body changes with progress of time with respect to a given frame of reference. Then with respect to that frame of reference, the body is in motion. And with respect to a frame of reference, the position of the body is not changing with progress of time. Then with respect to that frame of reference, the body is at rest. Okay, now I would like to repeat these two concepts once again. Rest and motion, it completely depends upon the frame of reference. That means with respect to a frame of reference, if a body is at state of rest or motion, it is not mandatory that the state of motion or rest need to be the same with respect to another frame of reference also. Okay, so that completely depends on the frame of reference. The next one is point object. If the distance traveled by the body is greater than, very greater than the size of the object, then it is treated as a point object. For example, if a train starts from Kashmir to Kanyakumari, fine, in that case, the train can be treated as a point object, isn't it? Yes. Next is one-dimensional motion. If we need only one coordinate out of x, y, z to represent the position of a body in motion, then that is said to be what? One-dimensional motion. For two dimension, that means out of three two coordinates will be changing with respect to time, that is two-dimensional motion. And definitely for three-dimensional motion, out of all the three coordinates, okay, and 3 out of 3 will be what? Changing with respect to progress of time. So one-dimensional motion out of 3, one coordinate will be changing. In two-dimensional motion out of 3, 2 will be changing, and in three-dimensional motion out of 3, 3 will be changing. Fine. Now next is distance or path length covered. The length of the path traveled by the body is treated as distance. Okay, and distance can never be a negative value. For a body in motion, distance is always keep on increasing, and distance is a scalar quantity. Unit is meter. Okay, now displacement, the shortest distance between the initial position to the final position of the body is known as displacement. Displacement can be positive, negative, as well as zero. Displacement can increase as well as decrease with progress of time. So that are the two important two important physical quantities that basically we used to tell about the regarding the position of the body. And the major importance where the major differences where I already told you, distance can never be a negative value, displacement can be positive, negative, as well as zero. Distance of a body in motion will always increase with respect to time, but displacement can increase as well as decrease with respect to time as well. And while comparing about while telling about the similarities, both are having same dimension and both are having same unit as well. Next is speed. The distance traveled in unit time is known as speed. Let's say unit is meter per second. All right. And next is uniform speed and variable speed. If the body travel equal distance in equal interval of time, then you may say that the body is traveling with uniform speed. And if the body covers unequal distance in equal interval of time or equal distance in unequal interval of time, in both the case you may treat that as a body traveling with non-uniform speed. Next one is average speed. Average speed is total distance upon total time taken. I repeat, total distance upon total time taken. And now here I have got few important relations which is very important for your examination, because this is again most frequent, this is an area where you can identify most frequently asked questions. So here, so the topic is basically the average speed. So two different cases we will be having here. The first one is the body is traveling equal distance, okay, with different speed. I repeat, S1 equal to S2 equal to E. That means two time intervals, two distance, two set of distance, that is S1 as well as S2, but both are the same. In that condition, how to calculate the average speed? Okay, the relation is 2 times V1 V2 upon V1 plus V2. And how it comes is, see, the distance traveled is S1, S2, S3, etc. All right. And what about the time taken? See, S1 distance was traveled with V1 speed, S2 distance was traveled with V2 speed. So the time is going to be what? S1 by V1. For that is T1 is going to be what? S1 by V1, and T2 is going to be what? S2 by V2. Am I right? So in that case, here it is going to be what? This particular part. If I am taking S1 as well as S2, this is going to be 2 times S all divided by S by V1 plus S by V2, and that's how we got this. Was that okay? Now, case number 2. Here the time interval is same. Here the distance was same. Here the time interval is same. All right. I repeat, here the distance was same and here the time interval is same. So here, if I want to take, again the concept is same, S1 and S2 is the total distance travel, time taken is T1 and T2. Okay. Now S1 is going to be what? V1 into T1. And what is S2? S2 is going to be what? V2 into T2. Here T1 as well as T2 are the same. So T1 and since T1 and T2 are the same, what will happen? This is going to be V1 plus V2 by 2, because T and T will cancel each other. On the denominator 2 will be left. So it's going to be V1 plus V2. So here, once the distance is same, it's going to be 2 V1 V2 upon V1 plus V2. And if the time is same, that is V1 plus V2 by 2. All right. Next is about the instantaneous speed. So in the last two slides, this one as well as this one, we were telling about the average speed, and here this is instantaneous speed. Okay. So at any particular instant, let the position of the body be X. And from there, we are providing a very small interval of time. And in that small interval of time, if ds is the distance traveled by the body, then ds by dt, that is what? The instantaneous speed of the body. And instantaneous speed means nothing that what we get from the speedometer at a given instant of time. Next is velocity. If total distance upon total time taken was the average speed, total displacement upon total time taken is going to be the average velocity. Okay, if displacement can be 0 as well as positive and negative, then definitely average velocity can be positive, negative as well as 0 for a body in motion. But for average speed, I repeat, distance can never be 0 for a body in motion, so average speed can never be 0. All right, and the same relation what I told there, average velocity is total displacement upon total time taken. Now instantaneous velocity is nothing, instantaneous speed mentioned along with direction. I repeat, instantaneous speed mentioned along with direction is instantaneous velocity. Okay, next is relative velocity. That means velocity of one object with respect to another one. That is known as what? Relative velocity. For example, velocity of A with respect to B. Here, velocity of A with respect to, that means velocity of A minus velocity of B. This is vector quantity, so I will be using vector symbol here. Velocity of A with respect to B, I repeat, velocity of A with respect to B is velocity of A minus velocity of B. Okay, now some special cases. Special case number 1, A and B moving in same direction. A and B moving in same direction. So the relative velocity is going to be VA minus VB. A and B moving in the opposite direction. All right, there it's going to be VA plus VB. And if they are at an angle of theta, so here you may say this is VA and here this is what? VB. In that case, the relative velocity of A minus velocity of B, the angle between A and B is theta. So there it is going to be the magnitude I am telling about. I am telling about the magnitude only. VAB, that is root of VA square plus VB square minus of 2 times VA VB into cos of theta. And what about the angle the relative velocity is going to make with respect to A? I repeat, with respect to A is tan of beta, that is going to be VB sine of theta upon VA minus of VB cos of theta, where theta is the angle that VB makes with respect to VA. Moving to the next, that is acceleration. Acceleration is rate of change of velocity. Here we are going to have acceleration as the standard expression is change in velocity upon time taken. Average acceleration means total change in velocity upon total time taken, and instantaneous acceleration means dv by dt. Both are having same unit, that is lt raised to minus 2. Okay, next is uniform as well as non-uniform acceleration. Average acceleration I already told you. Here we will be telling about that, I mean the basic relation in terms of A1 as well as A2, that I will tell you what it is. So uniform as well as non-uniform acceleration. Uniform acceleration means equal interval of time. During equal interval of time, the change in velocity is going to be equal. That means for delta t time, I repeat, for delta t time, if delta v is the change in velocity, for again another delta t time, it has to be what? Delta v only. Or I can say for another time interval of 2 times delta t, the change in velocity has to be 2 times delta v. Okay. Now, average acceleration, if the acceleration is a1 for time of t1 and here it is a2 for time duration of t2. So you all know that dv by dt, that's equal to what? A. All right. So the total change, like if d in this, from this one I can have dv as what? A into dt. So if a1 acceleration is there maintained for time duration of t1, so change in velocity is going to be what? A1 t1. And for time duration t2, it's going to be a2 t2, and total time taken is t1 plus t2. So in this case, you can have it as a average equal to a1 t1 plus a2 t2 all divided by t1 plus t2. Next is instantaneous acceleration. I already told you, if average acceleration a average, that is delta v upon delta t, then a instantaneous That's going to be dv by dt. Okay, next is graph. So first of all, we are going to have displacement time graph. Okay, first one is stationary body. So position is not changing. You can see the graph like this. Next is body moving with constant velocity. Here it's going to be a straight line. Okay, now it's moving with constant acceleration. I repeat, constant acceleration. So it's going to be like this. That means bent upward, constant acceleration. Next is constant deceleration. Okay, bend downward. Constant acceleration, speed is increasing. There it is decreasing. All right, and this is a case where which is not possible because at same for a given interval of time body is having multiple position. Okay, that is not possible. Now, what is a measurement that we can directly have from displacement time graph? We can have average velocity as well as instantaneous velocity from a position time graph. That is, let this be position time graph. So here the speed is increasing. All right, I mean speed is increasing for each unit of time. I mean we are having what? A positive acceleration. So speed is keep on increasing, increasing and increasing, not moving with a constant speed. Okay, it's increasing. Fine. So for given two time intervals, if I take the slope, here I will get what? Average velocity. And for a given instant of time, if I take the slope of this line, for two interval of time, I created a line and I took the slope of that will give average velocity. And here I am having a particular instant and I am creating a tangent to that, I mean the point that intersect over here. And if I take the slope, there I will get what? Instantaneous velocity. So from displacement time graph, we can calculate average velocity as well as instantaneous velocity. Okay. Next is velocity time graph. Okay. For a body in motion, the velocity time graph is like this. Moving with constant velocity, and here it is moving with constant acceleration. Here it is deceleration. In this case, initial velocity of the body is 0, and here the initial velocity is not equal to 0. All right. And in this case, you can have initial velocity as 0 but negative acceleration. Fine. And here initial velocity is 0, acceleration is there, that's moving in the upward direction. And here this is velocity time graph, acceleration is what? Negative. Here acceleration was positive, increasing acceleration. All right, here in all this case, in this one acceleration was what? Constant, positive. Here acceleration was again constant but negative. I repeat, here acceleration is positive, here acceleration is negative. Okay, and here body is starting from rest, negative acceleration. Body starting from rest, but acceleration is positive and increasing with time. And here the body is having non-zero value of velocity, acceleration is negative and acceleration is increasing with respect to time as well. That is why. Okay, now in this case, if I take the slope, the way we calculated slope here, from here also if we calculate the slope, I can have average acceleration as well as instantaneous acceleration from velocity time graph. That is point number 1. And area under velocity time graph, always remember, area under velocity time graph will give displacement. And if that area is considered along with the sign convention, you will get displacement. And if the sign is ignored, then you will get the total distance traveled. For example, let me take some space here. If I am having velocity time graph like this is VT graph. This area need to be treated as positive and this area need to be treated as what? Negative. So this area, that means A1 plus A2 is added by considering the sign, there you will get displacement. And if A1, the algebraic summation, if taken for A1 as well as A2, there you will get what? The total distance traveled. All right. Next is acceleration time graph. Case number 1, the body is moving with constant acceleration. As you can see that it's a straight line. Okay, here the acceleration is increasing constantly and here the acceleration is decreasing. Okay, and in this case, what we can calculate from this graph is area under acceleration time graph. Area under acceleration time graph will give change in velocity. I repeat, change in velocity, not velocity, change in velocity for two time intervals. Say for example, T1 and T2, this area will give what? Change in velocity for the time interval T1 to T2. All right. Next is equations of motion for uniformly accelerated bodies. We have got standard three expressions, and we will be having one more, that is the distance traveled in the nth second. The first one is v equal to u plus at. Next one is s is equal to ut plus half at square, and the third one is v square equal to u square plus 2as. Always keep one thing in mind. This is applicable only and only for body moving with constant acceleration. And if the body is having initial velocity as u and a as the acceleration, then the distance traveled in the nth second, I repeat, distance traveled in the nth second is s is equal to u plus a by 2 into 2n minus 1. I repeat, s is equal to u plus a by 2 into 2n minus of 1. Okay. Now students normally used to ask me, so sir, in units and dimension, you told us if three physical quantities are added together, okay, then all the three must be having same dimension. And here I can see s, and here you can see u. U stands for initial velocity. And here you can see s here. See, dear, all of you, please listen. Here this is not velocity. Here this was u multiplied by 1 second is there. Okay, so that is distance traveled in one for distance traveled u into 1, isn't it? So it's distance again, that u into 1, I mean 1 being the time, this is going to be again distance traveled only, so don't get stuck there. And the last point, that is a body which is traveling like something like a train, it's crossing a point like this. It was traveling the speed of v1 and it's accelerating, and the tail end, I mean the engine is the crossing that point speed v1, and definitely the guard room, that will be traveling at another speed. If the train is accelerating, let that be v2. Now the midpoint will be crossing this point with a speed that is equal to root of v1 square plus v2 square by 2. This was again a frequently asked case. Okay, that's why I separately said that. Fine. Now, uniformly accelerated motion. Uniformly accelerated motion means basically what? As the name says, acceleration is not uniform. Acceleration is not constant. Acceleration is varying, isn't it? Now, I have got something very, very important here. That is this particular expression. We all know that acceleration A, that is what? dv by dt. If I multiply this term with ds and divide this term with ds, and ds by dt is going to be what? ds, this is by ds, okay. ds by dt is going to be what? V only. So I can have the acceleration as A is equal to ds by dt is what? V into dv by ds. So that means if velocity is given as function of x, y, or displacements s, then acceleration can be also calculated from the expression v into dv by ds. I repeat, if v is given as function of s, then velocity is v into dv by ds, and if velocity is given as function of time t, then acceleration is a is equal to dv by dt. That is again a very, very important relation. And for a case where the acceleration is there in all the three directions, that means acceleration A has got its x component as ax, y component as ay, and z component as az. So definitely, once we split into its rectangular components, we can have it as ax I cap, ay j cap, and az k cap. In that case, ax, that is going to be d by dt of v suffix x, that is rate of change of velocity along x-axis. Ay is going to be rate of change of velocity along y-axis, and az is going to be rate of change of velocity along z-axis. All right. And the next is motion under gravity. All right. In this case, the acceleration experienced by the body is acceleration due to gravity. Here I have to tell you something very, very important. The point from where the motion starts, you need to take that as the origin. Okay. And now all measurements or all quantities from the origin in the upward direction, you must take it as positive, and all measurements from the origin in the downward direction, you need to take it as negative. All measurements from the origin towards right, you need to take it as positive, and all measurements from the origin towards left, you need to take it as negative. And I repeat once again, origin is the point from where the motion of the body begin. All right, so that need to be kept in mind while dealing with this section. Okay, now equations of motion, that is v equal to u plus at, s is equal to u plus half at square, v square equal to u square plus 2as is applicable here because acceleration is constant. Based on that, time taken to reach the maximum height, I repeat, time taken to reach the maximum height. At maximum height, the final velocity of the body is 0. So if I go for the equation v is equal to u plus at, the final velocity is 0. For a body which I am throwing from the origin in the upward direction, velocity is going to be u, that is in the upward direction, so it's going to be plus. Now acceleration experienced by the body is in the downward direction, that means from the origin acceleration is acting in the downward direction, so I need to mark it as minus of g and t. So I can have the time taken as what? U by g. That's how it came here, as u by g. All right, and always keep one thing in mind, the time taken for the body to reach to the top and the time taken for the body to come back, it's going to be the same. Based on that only we have calculated this, the time taken for the body to reach to the bottom. So there it's going to be what? Root of 2h by g. They calculated this from this expression, s is equal to ut plus half a t square. That means here we believe the body is dropped from a height h. I told you the time taken for the body to reach here and come back, it's going to be the same. Now I'm going to drop the body from the top. Okay, so displacement is minus of h in the downward direction, from the origin in the downward direction, and here this is half of acceleration is in the downward direction, so minus of g into t. So this negative and this negative will cancel each other, 2h by g under root, that's going to be the time taken. Okay, I hope you got it right. The next is, a ball is dropped from a building and the time taken for this ball to reach the bottom, that is small letter t. I repeat, the time taken by the ball to reach the bottom is t. And so here this is the building. Okay, height is h. First case, I am dropping the ball, that means u equal to 0. So now it reached here with a time of t. Now I am going to throw this ball in the upward direction with speed u, and at the same time I am going to throw another ball, okay, u in the downward direction. In the first one reach here in time of t1 and the second one reach here with the time of t2. Now how I can connect this t1 and t2 is, t is going to be root of t1 and t2. And the last point here is, if I drop a body from here, okay, that is u equal to 0, it will reach to the bottom within a time of say small letter t. And if I throw a body horizontally like this with a speed of v meter per second, the body is going to follow a path like this and it will reach here. The interesting part is, if the time taken by the body to reach from here to here, if it is t, then here also the time is going to be what? Small letter t. Next is motion in plane. The very first topic of this one is about the position vector, how to mention position vector once the motion is happening along a plane. We already discussed this in the very second chapter, I mean the previous one. There we discussed about motion in straight line, motion in plane, and motion in space, that is one dimensional, two dimensional, as well as three dimensional motion. There I told you, if only x coordinate is changing or y coordinate is changing or z coordinate is only changing, then we used to treat it as what? One dimensional motion. So here it is motion in a plane, that means out of three, two coordinates will be changing with respect to time. So just because of that, you can see here P is marked as the position of the object. Now that position is expressed in terms of x as well as in terms of what? Y. So x I cap and y j cap. X I cap and y j cap. That tells about what? the position of the body with respect to the origin. Now altogether if it is mentioned, I can have it as what? Xi cap plus yj cap, because this is the final position vector. And this final position vector, that is r vector, is a summation of xi cap plus yj cap. So that's telling about the position vector. And now at what angle, if you want to say at what angle the body is placed with respect to x-axis, so definitely this angle, if I take this as theta, now tan of theta is going to be what? Here tan of theta, that is going to be perpendicular by base. So perpendicular is y and base is what? X. So that is what mentioned over here. Are you getting me? Now moving to the next, that is how to take the magnitude of displacement vector. So as you all know, so here if it is mentioned as xi cap plus yj cap, to take the magnitude, definitely what need to be there? The magnitude of x square plus magnitude of y square, the all root. Okay, that means if initially it is marked as xi cap and yj cap, then the magnitude of position vector is going to be x square plus y square under root, isn't it? And here in this case, the position of the body is changing from x1 to x2 and y1 to y2. I repeat, x1 to x2 is the position is changing along x-axis, and y1 to y2 it is changing along y-axis. In that case, the magnitude of displacement vector is going to be root of x2 minus x1 the all square plus y2 minus y1 the all square. That is marked over here. Okay, again the same, to find the direction it's going to be delta y. Okay, tan theta is going to be delta y upon delta x, or theta is going to be tan inverse of delta y upon delta x. Okay, next is what about the velocity vector? You all know that rate of change of position is what? Rate of change of position is velocity. So velocity vector, since the motion is happening along a plane, the velocity also will be having two components, x component as well as y component. So we can represent the velocity as, see, in this here, velocity, the first I am going to tell in terms of average velocity, and in the slides ahead we will be having discussion related to instantaneous velocity. And if you want to represent average velocity first, definitely that is going to be what? Total displacement upon total time taken. And total displacement here it is taken as what? Delta r, that is r2 minus r1, where r2 is the final position vector and r1 is the initial position vector. Okay, now in that case it's going to be r2 minus r1 upon t2 minus t1, where t2 minus t1 is the time interval that we are providing. Now r2 minus r1 in terms of x and y, if I want to represent like that, then it is going to be delta xi cap plus delta yj cap. That is going to be the total displacement. Dividing that by time will give average velocity along x-axis as delta x upon delta t, and average velocity along y-axis as delta y upon delta t. And here this is the final expression for average velocity in form of its rectangular components. Okay, and the same technique is there. That means the technique that we use to get the magnitude of total displacement along x-axis as well as y-axis, the same thing I am using here as well. That is delta vx square plus delta vy square all root. That is going to be the magnitude of average velocity. So I mean to say is that, what I mean to say is, if average velocity, again if it is given in terms of rectangular components, you may have it as delta vx square plus delta vy square all root as magnitude of average velocity. Moving to the next slide, that is instantaneous velocity. You all know that instantaneous velocity, that means the velocity of any particular body at a particular instant of time. That means instantaneous speed along with direction gives instantaneous velocity. So here the general expression says that limit delta t tends to 0, delta r upon delta t. That is instantaneous velocity. That is nothing, dr by dt. Okay, again dr by dt, that is what? Velocity vector. And if again I want to represent this in terms of x component as well as y component, there it is going to be dx by dt I cap, that is going to be vx, that means instantaneous velocity along x-axis, and dy by dt, I repeat dy by dt, there you can see that is instantaneous velocity along y-axis. So here comes the expression for final instantaneous velocity in terms of x as well as y direction. So v vector, there is going to be vx I cap plus vy j cap, where vx and vy are instantaneous velocity along x-axis as well as instantaneous velocity along y-axis respectively. Again, I'm not repeating, but again and again, I'm not going to mention about the same. To get the magnitude of instantaneous velocity, you may again use the same technique. And to get the direction with respect to x-axis, if you want to find the direction, then tan theta is going to be what? Vy upon vx, or theta is tan inverse of vy upon vx. The next one is acceleration. Acceleration, as what we discussed in case of velocity, we separately explained average velocity as well as instantaneous velocity. In the same way, here we will be discussing about average acceleration as well as instantaneous acceleration. Average acceleration is again total velocity upon total time taken. Total change in velocity upon total time taken. Total change in velocity, we can have delta Vx as change in velocity along x-axis, delta Vy as change in velocity along y-axis, delta t is the time interval. Now, you may see here average velocity. Average velocity is delta Vx upon delta t along I cap plus delta Vy upon delta t along j cap, and to mark the magnitude, that is going to be average acceleration along x-axis, the whole square, okay, plus average acceleration along y-axis, the whole square under root will give the magnitude of average acceleration. Now, to take the direction, tan of theta is going to be a average along y-axis upon a average along x-axis. That is how we mark the direction as well. Now, coming to the instantaneous acceleration. Instantaneous acceleration, a is, first of all, let's start with the general expression. Instantaneous acceleration a, that is going to be dv by dt. And if we have got ax as well as ay as the component along x-axis as well as y-axis, then instantaneous acceleration a, that is ax I cap plus ay j cap, where ax is d by dt of vx and ay is d by dt of vy. And again, to get the direction, tan of theta is going to be ay upon ax, or theta equal to tan inverse of ay by ax. Okay. The next one is motion in plane with uniform acceleration. So here, in short, I would like to tell you, we all know that we have got three equations of motion, that is v equal to u plus at, v square equal to u square plus 2as, and s is equal to ut plus half of at square. Okay, now these three equations are applicable. You can take these three equations separately. You may consider this along x-axis, you may consider this along y-axis, as well as you may consider this along z-axis. Okay, so separately you can consider these three equations. For example, if you want to study the motion along x-axis only, how the velocity or acceleration or position is changing along x-axis only, then you may have the equation as vx is equal to u of x plus a of x into t. That is, final velocity along x-axis is going to be initial velocity along x-axis plus acceleration along x-axis into time taken. Now, final speed along x-axis, vx square, that's going to be square of the speed only. That is going to be ux square plus 2 times ax into s of x. That is v square equal to u square plus 2s. And next one is displacement along x-axis is equal to initial velocity along x-axis into time taken plus half of acceleration along x-axis into time taken square. S is equal to ut plus half of at square. In the same way, you may take it along y-axis, z-axis also. Alright, the entire thing is telling about that only. Fine. So now let me take you to the next. That is projectile motion. Circular motion we will be discussing after the laws of motion. So first, here we are going to discuss about projectile motion. All right. Now you all know that what is basically projectile. If I am having an object, okay, it is projected with a speed of u meter per second at an angle of theta. It is going to follow a path, and this path is known as the shape of this path is known as parabolic shape. Okay. So the body what we are throwing like this is basically known as a projectile. As far as projectile is considered, Okay, the most important topic that we need to understand from here is time of flight, maximum height, and the range of the projectile. Okay, so in all these cases, u cos theta as well as u sin theta component will appear. So u cos theta is nothing, the horizontal velocity component of the projectile, and u sin theta is the vertical velocity component of the projectile. And you know that for this case, this particular body is only experiencing one force, that is the weight of the body, which is acting in the downward direction. So acceleration due to gravity is the only acceleration experienced by the body, and that is acting along negative y-axis direction. There is no acceleration along x-axis. So if we separately consider the motion along x-axis as well as y-axis, the motion along x-axis can be treated as a uniform motion, and motion along y-axis is the only one which is going to be an accelerated motion. I repeat once again, motion along x-axis, that is going to be a uniform motion, all right, that is moving with constant velocity, and the motion along y-axis, that is going to be an accelerated motion. So that things need to be there in your mind. Now, while telling about the time of flight, the expression is coming as what? 2u sin theta by g. Okay, how that comes is, once it traveled from here to here, okay, once it traveled from here to here, and then later to here onto this particular portion, once it reached here, the final displacement along y-axis is 0. It reached from here to here and it reached here. Okay, so final displacement along y-axis is what? 0. That means displacement along y-axis is equal to initial velocity along y-axis into time taken plus half of acceleration along y-axis into time taken square. So for the complete flight, I am going to take small letter t as capital T, and that is what we got over here. Small letter t, I am going to take it as capital T. So I told you displacement along y-axis is 0, and here what was the velocity along y-axis? That was u sin theta. So I will be using that here. So the velocity along y-axis is u sin theta, that is in the upward direction, you can see. That's why here I am going to take it as what? Positive only, and time taken is capital T, plus half of, I told you here the acceleration is in the downward direction, so that is going to be negative. So I am going to have it as what? Minus of g into t square. Okay, so here these two will cancel each other, and solving this you will get this. Okay, and the time taken by the body to reach from here to here onto the top, that is exactly going to be the half of this. Okay, that means it's going to be u sine of theta by g. Okay, so the time taken by the body to reach from here to here is u sin theta by g, and for the complete journey it is 2u sin theta by g. All right, the next one is for the maximum height. There the expression is going to be u square sin square theta divided by 2g, and for the range it's going to be u square sin 2 theta by g. All right, the next one is some important points as well as formula. Okay, at any time, I repeat, at any time, if you want to find out what is the position of the body along x-axis, there you may have it as u cos theta into t. I told you along x-axis it is uniform motion. Velocity along x-axis is always constant since there is no acceleration. That means it is u cos theta into t. And at any time, if you want to find out the position, then you are going to use the equation here. It is s is equal to ut plus half at square only, where s along y-axis is taken as y. Initial velocity along y-axis is u sin theta, time taken is t, acceleration is acting in the downward direction, so half of gt square. And how to identify the equation of the trajectory? There you may have this particular expression, that is x tan y is equal to, I repeat, y is equal to x tan theta minus of gx square upon 2 times u square cos square theta. All right, this is very important. Direct questions were there many times related to this. Super important formula I would like to say. Okay, there were many times the questions were there, and identifying the trajectory of the motion. That means if x value is given, then you can immediately find out y value, or if y value is given, immediately you can find out x value, provided theta terms are given. So this equation will help you a lot. I repeat once again, here it is y is equal to x tan theta minus of gx square upon 2 times u square cos square theta. All right. Now, at any instant, if you want to find out the velocity, it's basically nothing, velocity along x-axis plus y-axis. Okay, now the kinetic energy at the lowest point, that is half of m into u square. Like you know that it's mv square is the general expression for kinetic energy. At the time of projection, it is having speed as small letter u. So the initial kinetic energy is given as what? Half of m into u square, and the initial linear momentum is m into v. Fine. And I already told you about regarding the acceleration, that is always g acting in the downward direction, and angular momentum, and this is again an important point. Angular momentum at any time, if you want to find out, is at any time, with respect to the origin. Say if h is the height, along x-axis, it's always going to have the velocity component as u cos theta only. So the angular momentum with respect to the origin, it's always going to be h into, where h is the height with respect to the origin, h into mu cos theta is going to be the angular momentum. Fine. And the next thing is regarding the time that I already told you. The time for the first half flight and the time for the second half flight is going to be the same. Okay. And the next one is regarding the maximum range of the projectile. Okay, the maximum range of the projectile is always going to happen if the angle of projection theta is equal to 45 degree, and you are going to get the expression for that as r max equal to u square divided by g. Okay, and when the range is maximum, I repeat, when the range is maximum, the maximum height is going to be what? R by 4. That is again an important formula. And the last one is, for two different angles, you can have the same range, that is theta as well as 90 minus theta. All right. So that were the important relation regarding the projectile motion. And now we are going to have a body projected horizontally from a particular height. For there, the time of flight t is going to be under root of 2h by g, where h is the height. Okay. Now the horizontal range of this one, that means this particular distance, that we call it as the horizontal range here again, and that is going to be what? u into under root of 2h by g. All right. Now at the time of landing, if you want to find out the final velocity, then that is velocity is going to be magnitude, I am telling here. Okay, that is going to be the magnitude of, so once it is landing here, it's going to be something like this. The velocity vector is going to be something like this. That means there it's going to have vx component as well as vy component. That vx as well as vy is marked here. So vx square plus vy square under root, that is going to be the magnitude of the velocity by which it's going to land onto the ground. And if you want to find out at what angle it's going to land onto the ground, I mean to say this particular angle theta, then tan of theta is going to be what? Tan of theta is going to be vy upon, tan of theta is going to be, in this case, if I am taking tan of theta is going to be vy upon vx, or theta is going to be tan inverse of vy upon vx. All right. And one more thing regarding the projectile, equation of projectile. Here this time y is equal to what? Gx square upon 2u square. Here there is cos theta is 0. That's why at the time of projection theta was 0. That's why in here we had an equation of projectile, isn't it? Okay, since theta is 0, this part will not be there in the final expression. So here you may see it as y is equal to gx square upon 2u square only. So that is going to be the equation of projectile in this case. All right, next is river crossing case. So let this be the river. Okay, two banks, and the river is flowing in this direction. So I would like to mark this as velocity of the river. All right, and I'm going to take the case of a boat crossing the river. So if the river is flowing like this with a velocity of vr, and if the boat is heading in this direction, initially, so this is vb, and here this is what? vr. Now you can see the boat is going to finally reach here. So this is what? The drift. This is the drift. Fine. So it's going to reach at this particular direction only. So if you want to find out at what particular direction it's going to finally reach, then I can say that tan of theta, that is going to be what? vr upon v suffix b, velocity of river upon velocity of boat. And if the boat want to reach on exactly the opposite point, okay, if that is the case what we are expecting, then in that condition, we must head the boat in this direction. So here this is vb. and here this is VR. Now here this is going to be velocity of boat with respect to the ground. That means it's exactly reach at this particular point. Now you can see this angle is what? 90 degree, and I am going to take this time this as theta. Now here if I want to say what is going to be that theta value, then tan theta is going to be what? VR upon VB. And with respect to the direction of flow of river, the boat need to be headed at an angle of 90 degree plus theta degree to reach on the opposite point. So this is the case of shortest path, and here this is the case in which the boat like we can cross the river in the shortest time. So here this is the case of shortest time. Here this is the case of shortest time, and here this is the case of what? Shortest path. This is a case of shortest path. And why this is termed as the shortest time, case of shortest time? Because we need a displacement along y-axis, and whatever I do have to invest along y-axis is only VB, because river velocity is already along x-axis. So river velocity is not going to contribute for our journey along y-axis. So what I only have to invest is my velocity component, that is VB. That means I'm treating it as a boat. I'm treating as the driver of the boat or pilot of the boat, whatsoever it may. Fine. Now VB can be entirely contributed along y-axis. That is the only possible way for me to cross the river at shortest time. So that is why this is treated as the case of shortest time, and definitely this is the shortest path. So that's going to be, that means the straight line is going to be the shortest path. So this is the case of shortest path. Then next one is rain man problem. All right, that means here let this be the direction of rain, VR. Okay, so if somebody is standing here and he or she want to protect themselves from the rain, that means they are supposed to keep the umbrella like this in the upward direction. Okay, now that means the umbrella need to be in the opposite direction of what? Velocity of the rain with respect to the man. And here in this case, this particular person is standing here. That means velocity of man is 0, stationary. In that case, you may hold it like this. And if this person is moving in the forward direction, okay, if this person is moving in the forward direction, that means, see, this is velocity of rain, all right, and this person is moving in the forward direction. So this is velocity of man. Now I told you velocity of rain with respect to man, that matters. That is going to be what? Velocity of rain minus velocity of man. So here the man is moving in the forward direction. So velocity of rain minus velocity of man means here this is minus of Vm. Okay, that means here this is going to be velocity of rain with respect to man. That means the umbrella need to be held in this direction. Fine. So umbrella need to be held in this particular direction. Now, if this is taken as theta, then tan of theta is going to be what? VR, that is perpendicular upon base, upon Vm. We are just telling about the magnitude only because we need this theta angle. So here, perpendicular side stands for the magnitude of VR and the base stands for the magnitude of Vm. There you may get it as what? Tan of theta. Now, if this person is moving in the backward direction, so obviously what? Here, if this was Vm, so Vm will be towards right. Okay, so that is the standard case. Multiple cases are there. Fine, for that detailed classes are there available in the YouTube. So moving to the next, that is laws of motion. Fine. Now here, first of all, we need to discuss about inertia of rest, inertia of motion, as well as inertia of direction. Okay, if the body is at state of rest, its tendency to continue in state of rest, that is known as inertia of rest. And if a body is in uniform motion, its tendency to continue in uniform motion, that means to continue with the same velocity, that is known as uniform motion. And inertia of direction, if a particular body is moving in a particular direction, its tendency not to change the direction, that is what we call it as what? Inertia of direction. All right, next one is force. Okay, so basically we must know about inertia in the beginning. Now, if force is acting, that is the one which is capable to take the bodies from state of rest to motion or motion to state of rest or the change in direction. That means here the tendency is going to be braked by whom? Force. All right. There are two type of force, that is contact force and non-contact force, field force, distance force. So many names are there. Contact force means there will be direct contact between the one who provide the force and second thing to the body that force is experienced. All right. In case of distance force, there won't be any direct contact. The best example that we can have is the gravitational force of attraction between the earth and the moon. There is no contact between moon and the earth, but still force is experienced by the moon because of the earth. That is why it is able to move. That means that is why it's able to orbit with respect to what? The earth. All right. So that was a best example that we can have. Now next is impulsive force. Impulsive force means a large force acts on a body for a small interval of time. That is what we call it as what? Impulsive force. Next is linear momentum. Mass multiplied by velocity stands for linear momentum. It can be represented as if a body is having mass m and velocity as v, then the linear momentum can be marked as m into v. Dimensional formula is mlt raised to minus 1. Okay. Next is law of conservation of linear momentum. Very important. Law of conservation of linear momentum says until or unless an external force, I repeat external force, internal force cannot change the linear momentum. Until or unless an external force is not acting on a body, the linear momentum of the body must remain always conserved. I repeat, only external force, internal force is not going to create any impact on the linear momentum of the body. Next is impulse. As I told you, impulse is nothing, it is change in linear momentum. If a force of F is acting on a body for a time of t, then the change in linear momentum or the impulse, we take it as force into time. So just based on this, one more thing you must understand. If ft graph is given, I repeat, if ft graph is given, and if you want to find out the change in linear momentum for a time interval from t1 to t2, so the area under the ft graph for the time interval t1 to t2 is going to be the change in linear momentum. And that is a very important information. Very important information. Next is Newton's first law. Newton's first law, you know that a body will continue in state of rest or uniform motion until or unless an external force is not applied. This is also known as law of inertia. Next one is Newton's second law. The rate of change of linear momentum is directly proportional to the force acting. Now linear momentum is m into v, so you may have it as f proportional to d by dt of m into v. In the case where mass is constant, so you may have it as what? F proportional to m into dv by dt. In case where velocity is kept constant and mass is continuously changing, exactly in the case of what we discussed in case of rock and all, we may have it as F proportional to v into dm by dt. In both these cases, the proportionality constant, that is k, is equal to 1 only. All right. Now force along x-axis, force along y-axis, as well as force along x-axis. Force along x-axis is rate of change of linear momentum along x-axis. Force along y-axis is rate of change of linear momentum along y-axis, and force along z-axis is rate of change of linear momentum along y-axis as well. All right. Next is Newton's third law. For every reaction, there is an equal and opposite reaction. That is basic statement. That means if two bodies are interacting, find like 1 and 2. That's what's shown here. 1 and 2. Now you can see a force is being experienced by 2 due to 1, that is marked as F21, and force is experienced by 1 due to 2, that is marked as F12. The magnitude of F12 and magnitude of F21, it's going to be the same, but direction is opposite, which means F12 is going to be minus of F21, and that minus says the direction is opposite. That's all. Okay. And most important thing, please don't forget, the magnitude is same, only direction is the different. So altogether, if we take this, the net force experienced by the system, I repeat, the net force experienced by the system is 0 because this is an internal force. Okay. The next one is modern version. The modern version says the body continues in its initial state of rest or motion with uniform velocity unless an unbalanced external force acts, and the second one force always occur in pair. Okay, that means the force experienced by A as well as force experienced by the B, force experienced by body B, both has got same magnitude, and altogether the net force experienced by the body is 0. All right. Next is the case of rocket propulsion. That means there, if the air fuel mixture is burned, all right, and that is thrown out from the rocket at a speed of u meter per second. All right. Okay. And the fuel burned in unit time is dm by dt. Now the force experienced by that particular part F, that means the contribution. Okay. The fuel, the contribution of the fuel that is burned out, and the force due to that one is going to be u into dm by dt. I told you in the previous case, here the rate of change of linear momentum F proportional to what? D by dt of m into v. And in this case, you can see u is kept a constant. That means here the rocket, this is the gas which is being ejected from the rocket, and that is ejected from the rocket at a speed of u meter per second, and the fuel that is burned in unit time, that is dm by dt. All right. So in that case, the force being experienced by this particular rocket, okay, that's going to be what? U into d by dt of m. Are you getting me? This is not the force, this is not the net force experience. This is the force provided by the engine. That is the only thing. Other than that, weight is there. So if you want to get the final expression, I can say that m into a upward. That means the net force experienced in the upward direction. That is, this is the thrust. That means the upward force being provided by the body. That is u into dm by dt minus of m into g. This can be the final expression. All right. Next is equilibrium. If a body is at equilibrium condition, that means the net force experienced by the body is zero. That is, force along x-axis plus force along y-axis plus force along z-axis is equal to 0. Then we can say that the net force experienced by the body is 0, and that condition is known as what? Equilibrium condition. Okay. Now another case of equilibrium condition there where three forces are acting, like F1, F2 and F3 is acting, and the angle is marked as alpha, beta and gamma. That is, force between 1 and 3, 2 and 3 it is marked as alpha, and 1 and 3 it is marked as beta, and 1 and 2 it is marked as alpha. Okay. And one more easy thing I would like to tell you. F1, opposite of F1 is alpha, opposite of F2 is beta, and opposite of F3 is gamma. If that is the condition, and if the body is at equilibrium, then F1 upon sine alpha will be equal to, this is not there, F1 upon sine alpha equal to F2 upon sine beta equal to F3 upon sine gamma under equilibrium condition. And this is what we call it as what? Lami's theorem. So this was about equilibrium. For equilibrium condition means the net force experienced by the body will be 0. All right. That is all. The next one is some common terms that we are going to deal with, especially related to the force. Is first one is weight. The force exerted on any body due to the gravitational pull of Earth, that is known as the weight. That is basically m into g. Next one is normal reaction. That means if you keep a body on any particular surface, okay, so due to the weight of the body, there will be a force acting, that is m into g. And now this is force acting on 1 due to 2. I repeat, force acting on 1 due to 2. Now 1 will be giving a force, it will be giving its reaction. If m into g is the action, it will be offering a reaction, and that reaction is known as what? Normal reaction. And as the name indicates, that always act perpendicular to the surface of contact. Okay. Next is tension. If we are pulling a body using a massless string, okay, then the force developed on that is known as a tension. All right. So I said it is a massless string. If you have a string with having mass also, there also it will be having a tension. Why I said massless string is, immediately after this I wanted to give you an expression. That is the only reason I said it is a massless string. So if T is the tension developed in the string. Now if this mass is moving with an acceleration of a, then I can say that m into a is equal to the tension. So just to tell about this only, I said it as a massless string. Okay. Now the next is, what happens to the weight of the body if it is kept inside a lift and the lift is moving in the upward direction, downward direction, accelerating in the upward direction and accelerating in the downward direction? I would like to tell you in short, if the lift is kept stationary, definitely the weight, and before that, weight is nothing. It purely depends on the normal reaction. All right. Weight is the measurement what we are getting from the measuring device. And how the measuring device gives the reading? it sends the normal reaction. So normal reaction is what the weighing machine is going to identify, and based on that only we are going to get the measurement reading for the weight. Okay, now if mass is kept on the lift and the lift is stationary, then normal reaction is equal to m into g. And if the lift is moving in the upward direction or in the downward direction with a constant velocity, there also, since there is no net acceleration, mg is going to be n only. That means n means weight. Okay, n means, as per the machine, n means the weight. Again, n is going to be m into g. And if this is moving in the upward direction with an acceleration of a, if it is moving in the upward direction with an acceleration of a, there you can have m into a upward. That is normal reaction in the upward direction minus of m into g. Here I can say that n is equal to what? M into a plus g. And I told you n is what we are going to get as the weight. Now here you can see the weight of the body is increasing. And if the lift is coming down with an acceleration of a, then I may have the equation as m into a downward. That is m into g downward minus normal reaction upward. Here normal reaction is going to be n equals m into g minus of m into a. That means here the weight is decreasing. Normal reaction is decreasing, which means weight is decreasing. And if this body is coming freely, this lift is allowed to fall freely, in that case a is going to be what? G. A is going to be g. In that condition, the normal reaction is going to be 0, and that condition is known as weightless condition. So weight from a measuring device means normal reaction. All right. Next one is the frictional force. Whenever a body is trying to move over another on a surface, that offers what? Friction. All right. And frictional force is always proportional to the normal reaction, and it depends on one more thing that is known as coefficient of friction. All right. And here in this case we are going to have, so static, the classifications comes as static friction and limiting friction. So static friction means whenever there is a body kept over and we are applying a force, okay, and if this body is not moving at any time, the friction developed is basically known as what? Static friction. Okay, and if you keep on increasing this force, okay, if you keep on increasing force, okay, all of a sudden it won't start moving. You keep on increasing the force, it keep on increasing, and at a particular moment, it will just start moving. Okay, that means just before that there was a maximum value, isn't it? And that maximum value is known as what? Limiting friction. All right. Okay, so the limiting friction is normal reaction n, which is equal to m into g, okay, for a horizontal surface. So the limiting friction, that we call it as maximum of static friction, that is always equal to coefficient of friction between two surfaces multiplied by the normal reaction. All right. So what I mean to say is that if the limiting friction of a body is 10 Newton, if the limiting friction of a body is 10 Newton, and if somebody is applying a force of say 2 Newton, so here the frictional force also is going to be what? 2 Newton only. All right. So please come out of that misconcept that if mu is the coefficient of friction and n is the normal reaction, frictional force is always equal to mu into n. No, it completely depends what is the force being applied or exerted by the external agent. So that is a super important area. Next one is angle of friction as well as angle of repose. So regarding that, I would like to explain it in this way. Let this be the normal reaction. Let an external agent is applying a force like this, and as a result of that there is a frictional force in this way. So the resultant of normal reaction as well as the frictional force is going to be this R. I repeat, resultant of normal reaction as well as frictional force is going to be this. So here I can say theta. Okay, that is tan of theta is going to be what? Tan of theta is going to be F upon N. And here theta is known as what? Angle of friction. Next is angle of repose. Let me have a body kept on an inclined surface like this. Let this be theta. And the theta is increased such a way that the body just start moving. That means m into g sine theta acting in the downward direction is equal to the frictional force here. And you know that here this is mg cos theta. If mg cos theta is acting like this, which means normal reaction is equal to mg cos theta. So here the frictional force is going to be mu into mg cos theta. The case where the body is at equilibrium, I can say that mg sin theta is equal to mg cos theta. Mg and mg will cancel each other. Now sin theta by cos theta, that is going to be tan theta. And tan theta is going to be what? Mu. So this is the maximum inclination what I can have without the body sliding in the downward direction. So that particular angle, that is known as angle of repose. And how we connect angle of repose as well as coefficient of friction is tan of theta is equal to mu. All right. The next one is kinetic friction. The friction force offered experienced by the body once one body is moving over the another surface. The previous one, the body was not moving. Here it is moving. So that case is known as kinetic friction. And how that varies, mu is going to be replaced by mu suffix k. And here this is coefficient of kinetic friction. And here this was coefficient of static friction. And once the body is moving, there the chances of two type of friction is there. First one is sliding and another one is rolling friction. Rolling friction is the one which is having the least magnitude. That means the rolling friction is lesser than the sliding friction. All right. So that was all about the frictional force experienced by the body in motion. And the next one is motion on a rough inclined plane. So in this case, the body was not moving. Here it started moving along a horizontal surface. Now it's here I am having the body which is sliding along an inclined plane. So here, if I consider the inclination as theta, the downward force acting is mg sin theta, the upward force is, that is frictional force, that is mu into mg cos theta. So at equilibrium, it's going to be the same. I means mg sin theta is going to be f at equilibrium. And if the body is moving in the downward direction with an acceleration of a, then I may write the equation as m into a downward, that is equal to f, that equal to downward force, that is mg sin theta minus the frictional force f. And you may mark frictional force as mu mg cos theta. All right. So the special cases are given here. There is minimum frictional force to move the body in the upward direction and minimal force required to push the body in the downward direction. So minimum force to push the body in the upward direction is going to be mg sin theta plus mu mg cos theta, because frictional force as well as the gravitational component, it is acting in the downward direction once we are pushing in the upward direction. So that is why you may have mg sin theta in the downward direction and mu mg cos theta also in the downward direction. So opposing these two, we need to apply a force in the upward direction. It's coming like this. And if you want to push a body in the downward direction, all right, okay, downward direction. So already you are having the benefit of mg sin theta in the downward direction. So the external force that we need to apply, F2, that is going to be m into g times mu cos theta minus of sin theta. G came out, that is why it is m into g, that's common. And what you are left is mu cos theta minus of sin theta. That is the net force that we required in the downward direction. So this was pushing in the upward direction, and here this is pushing in the downward direction. Both are minimum force. Don't forget, both were the minimum force required to push upward and push downward. Okay. Next is bodies in contact. So here I have got M1 as well as M2 connected in, like they are in contact, and an external force F is applied, and the system is moving towards right with an acceleration of A, isn't it? So I can have the final expression as F is equal to M1 plus M2 into A. So here the acceleration experienced by the body, that is going to be what? F upon M1 plus M2. And if you want to find out the normal reaction between this, the best method is just take M2. Just take M2. Normal reaction is N. This is experiencing an acceleration A towards right. Now I can say the normal reaction N, that is mass of the body, that is M2, okay, into acceleration, that is F upon M1 plus M2. All right. In the same way, you can consider this also. That means here three masses are there, M1, M2 and M3. So force is equal to what? M1 plus M2 plus M3 into A. Here acceleration is going to be what? F upon M1 plus M2 plus M3. Fine. If you want to find the normal reaction here, first of all, you need to consider M3, and M3 into A is going to be N. And if you want to find out the normal reaction here, you need to consider these two mass. That is m2 plus m3 into A. That is going to be the normal reaction here. Okay, I believe you got the technique. Fine. The next is body connected by string. Here you have got M1, M2 and M3 all together being pulled by a force F. And here the strings are massless string. Okay, and you know that here the tension will be there. Now again, as what we discussed in this case, okay, three masses are moving with same acceleration. That means M1 plus M2 plus M3. It's moving with an acceleration of A under the influence of this force F. This will give you the expression for A. If you want to find out the tension here, you take the mass towards the left. That is M2 into M3. Now M2 into M3 is moving towards right. M2 plus M3 is moving towards right with an acceleration of A under the influence of T2. If you want to find T3, M3 is moving towards right with an acceleration of A only under the influence of 3. So M3 into A is happening because of what? T3. I believe you got it right. The next one is pulley mass system. Fine. Here you have got a pulley, and over that, with the help of an inextensible massless string, I am having M1 as well as M2 here. Here the condition is M1 is greater than M2. I repeat, M1 is greater than M2. Now this system will be moving like this. Okay, M1 is going to come in the downward direction and M2 is going to move in the upward direction. Now this particular system is going to have the net acceleration as M1 plus M2 into A. That is just because of the downward pull due to M1 minus opposing pull due to M2. So here this is going to be M1 minus of M2 into G. Alright, so if you see the acceleration, you may have the same expression here. Okay, that is M1 minus M2 to G upon M1 plus M2. Now, if you want to find out the tension in terms of say M1 or M2, tension is going to be the same. Okay, whether it is here, the tension is going to be same because it's a massless string, isn't it? So, if you want to find out the tension in terms of M2, I can say that M2 into A upward, that is T minus of M2G. And if here in terms of M1, if you want to say, I can say that M1 into A downward, that is equal to M1G downward minus of T. That's it. And you have the expression for A here. The same thing is applicable here as well. If there is no friction, and if the friction is there, you need to just consider the opposing force, that is M2G. That's the only thing. You have got the detailed expression here. Okay. And the moving to the next, that is over a smooth inclined plane. And if you're having a smooth inclined plane, here I have got a mass M2 kept over here as well as M1 kept over here. For M1, M1G is acting in the downward direction and T is acting in the upward direction. For M2, M2 times G sin theta is acting in the downward direction. Here there is M2 G cos theta. Alright. Now if you want to write the expression for this particular body moving in the upward direction, I can say that M2 into A upward, that is equal to T minus of M2G sin theta. And if I consider the expression for this, I can say it as M1 into A downward, that is going to be M1 into G downward minus of T. Solving these two, you will get the expression for tension and acceleration. Alright. And the next one is motion of two bodies. The concept is the same thing. There, if it was M1G acting in the downward direction, so here I need to separately consider M1G sin theta 1 as well as M1G cos theta 1, and here it is M2G sin theta 2 and M1G cos theta 1 need to be there, and you need to consider the force along this direction as well as force along this direction. Solve this equation, you will get the expression for acceleration as well as time. It is the same technique that we used over here, the same thing you can apply here as well. Alright, I repeat once again, resolve the force, apply it along this direction as well as along the downward direction. Two equations you will get, just solve that and you can reach on to this particular expression for acceleration as well as time. Okay, the next one is circular motion. So if a body is having an angular displacement, say theta, and after dt time interval, it goes through an angular displacement of d theta, then you know that d theta by dt, we call it as what? The angular speed. All right, and d by dt of omega, that is what we call it as the angular acceleration, isn't it? Now that is what mentioned over here, angular velocity. Okay, and here this is angular displacement. And what is the relation between tangential velocity component and angular velocity component? That is v is equal to r omega. I repeat, v is equal to r omega. Here this is the tangential velocity component and here this is angular velocity component, and r is the radius in which the body is moving. All right, next is about the relation between linear acceleration as well as angular acceleration. That is a is equal to r alpha, and here you have got the relation between angular acceleration as well as linear velocity. That is what? A is equal to v square by r. Centripetal acceleration, basically this is, here this is v, okay, and here this is r, and here this is the centripetal acceleration, so this need to be small letter a. Centripetal acceleration, that need to be what? V square upon r. All right, okay. Next one is non-uniform circular motion. Non-uniform circular motion means, here in this case, you know, the body was moving with constant velocity. Fine, the body was moving with constant velocity, so only one acceleration is there. There is centripetal acceleration and we call it as what? V square by r. In this case, what happens is the speed of the body is increasing. Speed of the body is increasing. That means it is going to have a tangential acceleration and this is going to have a radial acceleration also. So radial acceleration is one which is responsible for changing direction, and tangential acceleration is the one which is responsible for the change in speed. Now tangential acceleration at, that is d by dt of v, the rate at which the speed is being changed. And radial acceleration, at any time if v is the speed, then radial acceleration ar, that is going to be what? V square by r. And the resultant acceleration is going to be what? Square of tangential acceleration plus square of radial acceleration under root. That is going to be the resultant acceleration experience. All right. Now here these are the equations of motion, and along the equations of motion for circular dynamics. So here we know the expression v is equal to u plus at, v square equal to u square plus 2s, and s is equal to ut plus half at square. The same thing is applicable in case of what? Circular motion also. Final angular velocity is equal to initial angular velocity plus angular acceleration to time taken. Now angular displacement, theta is equal to initial angular velocity in time taken plus half of angular acceleration to time taken square. Final angular speed square means omega square equal to omega naught square plus 2 times alpha into theta, and here this is the angular displacement in the end the time, and here this is the average displacement. All right, and the next one is centripetal acceleration. We already discussed about this. Now centripetal force, if centripetal acceleration is v square by r, now mass multiplied by centripetal acceleration, that will give the centripetal force. You may have it as F is equal to mv square by r, and if you want to replace v in terms of omega, then you may have it as what? M into r omega square. So that is this particular relation. Next one is centripetal force. We already discussed about this. Now the case is circular turning. That means if a body is moving in a circular path, the force that this body need to keep itself in a circular path is centripetal force, and in this case the centripetal force can be offered by the friction between the floor. I mean, if it is a car, then it's going to be a friction between the tire of the car as well as the road. So based on that, you know that the friction has got a maximum limit. Beyond that, it cannot offer a force, isn't it? So that means based on that, if force has got a limitation, that means speed also definitely will be having a limitation, because this centripetal force is offered by the friction, and if the speed increases, friction also will increase, and friction force can't increase beyond a limit. So based on that, I can have the maximum speed. Maximum speed is v equal to, I repeat, the maximum speed v is equal to root of mu rg. Okay, that means for a safe turn, v need to be less than or equal to under root of mu r into g. Okay, and if there is no friction, then also we can manage the situation, but by providing a banking of theta, and there v is going to be a root of r into g into tan theta, where r is the radius of the path. All right, and if there is a case where inclination is offered, I mean banking is provided and friction is also there, in that case v max is going to be root of r into tan of theta plus mu suffix s, is friction, coefficient of friction upon 1 minus mu s into tan of theta. So this is the case where banking plus friction is being offered. Next is the case of bending of a cyclist. That means if the like somebody is taking a turn on a cycle, for a safe turn, the banking need to be for an angle of theta. And how we can have the relation between theta and the speed v is tan of theta is equal to v square upon r into g, where v is the speed and r is the radius of the track. So that was all from my end for this time. Meet you soon with another detailed video. Till then, bye bye and take care.